Hi, welcome to the third video in our brief electrochemistry unit. This one's going to be on what's called electrolysis. Unlike the previous two videos on voltaic cells, cells that work sort of naturally based on one element's pull on electrons compared to any other ones, electrolysis is actually using a direct current of electrons, a flow of electrons, to actually cause a reaction that would normally not happen. So a key idea here, so using a flow of electrons to cause a reaction, and the term we might normally say here is unfavorable. The idea simply being that batteries work favorably. They just sort of naturally work. You put two elements together, one of them is better at taking electrons, and so it does. But if I wanted the element that's not as good to take electrons or to cause a reaction that normally wouldn't work, one way I can do it is throw a whole bunch of electrons at it and see what happens. And what happens a lot of the time is that you can actually reverse the reaction, run it backwards. So essentially, that's kind of the idea behind rechargeable batteries, is essentially you plug it in, and between the amount of electric potential and the flow of electrons that comes in, you can actually charge your battery back up. Even though it is naturally depleted, you can sort of unnaturally recharge it. And there's a concept that we'll talk a lot more about in the next unit about favorability, or what's called, used to be called spontaneity, now generally referred to as thermodynamic favorability or unfavorability. So here we're using a flow of electrons to cause an unfavorable reaction, something that would not normally work. A key idea is that voltaic cells, voltaic cells work favorably. They sort of naturally work to generate electricity. And so if I'm trying to reverse that process or to do other reactions, this is going to be an unfavorable thing, and it takes energy or electricity, or which really is a form of energy, to reverse that process. So, but we'll talk more about that, but kind of bear that in mind. So they work favorably. They have a tendency to move to the products. That's kind of a key idea to keep in mind. Maybe you could tie this together with your understanding of equilibrium. If they're naturally moving towards the products, what might the K value be for equilibrium reactions? Is it less than 1 or is it greater than 1? So essentially then what we've got then is, when we get down to it, is simply a math problem. When we do electrolysis, essentially what we're doing is dimensional analysis. So these problems are essentially just not even very long ones, but there's just a lot of terminology that's unfamiliar. So these are essentially just dimensional analysis problems. So I just kind of want to go through some of the terms to kind of get us started on solving these. Then we'll do a sample problem. And that should leave you in good enough shape to be able to kind of think about this as we go. But some of the things that we might use electrolysis for, as we'll talk about, one of the main ones is electroplating. So the root of electrolysis is using electricity to lyse something, which is to break it apart. But essentially, we're going to be talking mainly about the idea of electroplating, which is one of the uses that came later throughout history, is that scientists realized that you could actually coat things in thin layers of other metals that could not normally be formed in that manner. And so using that unfavorability to the advantage of coating maybe an unsort of favorable, like a metal that's likely to corrode, with one that isn't, but a thin coat of it. So it's sort of a thin protective layer. So we'll talk about that sort of thing. So the main idea here then with these unfamiliar terms is that we're going to be talking about terms like current. That's one of the unfamiliar terms. That's simply a flow of electrons. And it's measured in coulombs per second. We've talked a lot about the coulombic forces, so we're talking about the same idea here, which is simply the coulombs are a unit of charge. And so we're talking about the amount of charge per second that flows along a wire. So the idea then simply is we have a certain amount of electrons flowing along a wire every second. The more electrons we have, the higher the current. Each electron has a certain amount of charge. So Coulomb simply a measure of charge per second then essentially. And electrons carry that charge. But each electron, being so tiny, doesn't have a whole lot of coulombs. In fact, one electron has a charge of about 1.6 times 10 to the negative 19th coulomb. So very, very little charge on one electron, but we rarely, if ever, deal with simply one electron in reactions. We deal with a whole bunch of them. So we tend to talk about a lot more of them. And in fact, we usually talk about 96,500 coulombs. That is a mole of electrons. Maybe I'll back that up and we'll kind of do this to format it the same way then. So 1 mole of electrons, if I simply take Avogadro's number and multiply it by this 1.6 times 10 to the negative 19th, I get around 96,000, technically 485 coulombs, but we'll just round it to 96,500. That's known as Faraday's constant. And Faraday is pictured here. That's him right there, Michael Faraday, in many ways the kind of founder of our modern understanding of electricity, just a legendary figure in the history of science. His signature I included there below. Oftentimes this is just abbreviated now as capital F, but it used to be sort of labeled something along these lines, which sort of looks a little bit like the F in his signature, but the font for that is rarely used anymore, and they almost always just use regular little capital F, which is something to bear in mind. So 1 amp, you've probably heard that term, 1 amp, which is usually just abbreviated as 1 capital A, is equal to 1 coulomb per second. So current is measured oftentimes in amps, and you may have heard that term here and there, not as an amplifier for you music files, but simply just as a measure of current. It doesn't take much current, just so you know, if you apply current to the body, to have very negative consequences. So anywhere in the milliamp range, so half an amp, a quarter of an amp, just kind of depending on the situation, whether the wire's touching a certain part of the body or whether it's direct current or alternating current, so DC or AC. But anywhere south of an amp can start to cause damage, and certainly as you get close to 1 amp, it can be very certainly lethal. Half an amp is usually a heart-stopping amount of current to have applied to the body, and so a full amp is really quite dangerous. And so if you think about a mole of electrons, which is 96,500 coulombs, if a mole of electrons were delivered to the body would likely not survive. That's an immense amount of charge to throw at your body. So when we talk about amps, 1 amp is a very large amount of current, although it's not very many moles of electrons. And so we're going to kind of talk about that as we go through some of these math problems. So just kind of bear that in mind as we go. So we have 1 amp is a coulomb per second. And so usually what we'll have then is a unit of time. How long did it take for this current to be applied? We'll have the current in amps, and we'll have the substance, and that substance necessitates a certain number of electrons, and we'll kind of follow it from there. So let's look at a simple classic problem. They're really not too difficult to solve. As I say, they're essentially dimensional analysis problems. So let's say that steel is used in metals, but due to its propensity to rust, it's usually coated in some other metal to keep it a little bit safer. So its rusting propensity is often covered in other metals. So the way that we do that is simply, as I mentioned earlier, by electroplating it. So if some steel is placed in a bath of zinc 2+ ions and a current of 1.5 amps, so a very dangerous amount of current, but again, not much in the way of moles of electrons, is applied for 20 minutes, how many grams of solid zinc will plate? So what amount of solid zinc will we have deposited on top of this piece of steel? So again, this is really just a dimensional analysis problem, and there's a couple of constants and things like that that we'll kind of throw in. But really, if you start in this particular direction, we'll maybe talk about how to do a problem in the reverse direction, but usually this is the way that they work. If you start with the unit of time, you can kind of work your way from the beginning to the end of the problem. So if we start with 20 minutes, we'll convert it to seconds, and the reason we would do that is because amps are measured in coulombs per second, so 1.5 amps is simply 1.5 coulombs per second. So for our minutes and then our seconds will have divided out, and we just have the amount of charge. So essentially that means in the 20 minutes that we ran this current into it, this is the total amount of coulombs that will have arrived in the bath. So if we do 20 times 60, that's 1200. 1200 times 1.5 is 1800. So 1800 coulombs arrived in the bath over these 20 minutes. Again, that's a lot of charge, but not much compared to moles of electrons. So there aren't many moles of electrons, and we can figure out how many moles of electrons they are because of Faraday's constant. So 96,500 coulombs. That'll tell me not just how many coulombs I have, but more importantly for what we're doing, how many moles of electrons we have. So the 1800 coulombs will be divided by the 96,500 coulombs. That would tell me how many moles of electrons were delivered to the bath in these 20 minutes. And then the key idea, and this is where people get tripped up a lot of times, is that each zinc, so in order to make one solid zinc from zinc 2+, one zinc takes 2 electrons. So each and every zinc 2+, and you can either write this as zinc or zinc 2+, it doesn't really matter. Each one of them needs 2 electrons, so we have a 1 to 2 relationship. In other words, I get half as many moles of zinc as I have electrons because each zinc needs 2 electrons. And so if you think about this, we now have moles of zinc. And the last step is simply to multiply by the molar mass of zinc. That many grams per mole. And when you do that, you get actually a rather paltry figure, 1.22 grams of zinc. And the reason it's rather paltry is, again, because even though that's a large current in terms of danger to living things, it's not much when it comes to moles of electrons. And so it would actually take quite a while of running this, or you'd run it just at a much higher current to try to make it go faster. The flip side of that, in some ways, though, is you don't need a lot of zinc to coat something. You can actually get these very, very thin coatings. When you electroplate something, you can actually get away with a pretty thin coating because even a thin coating to our macroscopic world is a lot of atoms thick. And usually if a coating is a lot of atoms thick, it provides the protective properties that you're looking for. So that 1.22 grams of zinc, obviously depending on the size of the piece of steel, might go a lot farther than you think to coating it safely. Other problems, again, sometimes they'll say for how long must the current need to run, or what current would be needed if it were to run for a certain amount of time, and they're just kind of working the problems backwards. So not too tricky there. So again, just a dimensional analysis problem. There'll likely be one for your homework, but it'll look pretty much identical to this sample problem. All right, I hope that makes sense. If it doesn't, of course, there's always office hours, and we'll do the best we can to work through this, but I hope this was a particularly electrifying video. All right, we'll talk to you in the next one, and we're going to probably move on pretty soon to thermodynamics. Have a good day.